I'm glad to present you spectroscopic ellipsometry for in-depth optical and structural profiling of photochromic yttrium oxyhydrides in films. This is the outline of my talk. I will give an introduction about yttrium hydroxide, what it is and what issues this material is presenting. Then I will give an introduction about spectroscopic ellipsometry, its principles and applications for yttrium hydroxide studies. And then I will provide 3 examples where ellipsometry is applied for yttrium hydroxide analysis. Yttrium hydroxide analyzed with fabricated with A-beam evaporation, then yttrium hydroxide fabricated with pulsed DC magneton sputtering, and then some examples also for time result spectroscopic ellipsometry and photoactive dynamics. So let's see now what is yttrium hydroxide. Yttrium hydroxide is a mixed anion compound that combines hydrogen and oxygen ions. It shows photochromism, meaning its darkness reversibly when exposed to UV light or blue light. Under illumination, its transmittance can drop from over 85% down to 20%. Importantly, it operates under ambient conditions. That means that we don't need heat or external electric field to activate this material. This makes it a strong candidate for smart windows and building facilities. Yttrium hydroxide has a face-centered cubic structure made up of yttrium atoms. Both hydrogen and oxygen atoms sit in the tetrahedral interstitial sites of this lattice. This specific position of hydrogen and oxygen ions plays a key role in shaping the electronic structure and drives yttrium hydroxide photochromic behavior. Now let's see what key gains and pains have this material. On the plus side of this material is that it shows photochromism under normal atmospheric conditions. That means we don't need to give a heat or electric field. It also offers a high transparency contrast from 85 down to 20%. It's a non-toxic, rare earth-based material, making it more environmentally friendly than some of alternatives. It's compatible with scalable deposition technologies like A-beam evaporation and DC magneton sputtering. And so it could be applied also to make, for example, large area coatings. But still we have some problems with this material, some challenges. For example, its switching mechanism is still not clearly understood. Its bleaching is slower under oxygen-free environment, which limits its recovery. And it has also problems with its adhesion. For example, it is quite normal to observe delamination of thin films from the substrates during many cycling. The material is very sensitive also to composition. Small changes can affect performances, and long-term stability under repeatable switching remains still a big concern. Here, ellipsometry offers a non-destructive way to assess film quality and present in detail the properties of the film, which can become a very valuable tool for optimizing sputtering parameters to achieve higher quality films. So now let's see what is spectroscopic ellipsometry. Ellipsometry is a method which measures the polarization change when light reflects from the surface. It uses P and S coordinate system relative to the sample plane of incidence. Ratio of P-S reflectivity, which are complex Fresnel reflection coefficients, are related with the main ellipsometric angles called psi and delta. As you can see in this formula, it expresses the psi and delta relation with Fresnel reflection coefficients. What we can see from this formula basically is that psi is the amplitude of ratio, delta is a phase of ratio, and rho is a complex reflectivity ratio. The main ellipsometric angles psi and delta are directly linked to these Fresnel equations. This means that they are fundamentally linked to the complex refractive index and thickness of the films or bulk substrates, or any inhomogeneities they may have. When analyzing multi-layer structures, it's important to account for all individual layers. Each one is contributing to the light interference and affects the reflected signal. In case we are doing in situ spectroscopic ellipsometry, situation is becoming even more complex because we have to take into account also time, for example, applied field, or temperature, or pressure. So all this is pretty difficult. So ellipsometry definitely is not the most simple experimental method. This slide is interesting in the sense that it highlights the key advantage of ellipsometry. It's independent of light intensity. It is very fascinating. While intensity refers to the amplitude of size of electric field, ellipsometry measures polarization, which describes the shape of how the electric field travels. Since the polarization measurements are unaffected by changes in intensity, ellipsometry remains highly accurate and reliable even if there are any light source fluctuations. Here you can see the model-based regression analysis workflow used in a spectroscopic ellipsometry, because in ellipsometry it's not enough just to make experimental measurement of psi and delta, which is a function of wavelengths or photon energy. We have to apply a model to understand how these psi and delta are describing our sample. Here you can see this approach, which consists of following steps. So we start with measurement. It is experimental data such as psi and delta spectra as a function of incident angle, or even some other parameters like applied voltage or temperature in case of in situ ellipsometry. And we do this scan over the wavelength range. Then we perform the model creation. It is a physical model constructing using parameters such as optical properties of our sample, thickness, roughness, and any inhomogeneities or anisotropy in case of anisotropic samples. This model is used to simulate the experimental optical response, generate the data. And then we do fitting. The simulated data are compared with the experimental measurements. The model is iteratively refined to minimize the difference between the measured and calculated data, the so-called regression analysis. And then we arrive to the results. Once the best fit is achieved, the model yields a material and structural parameters, and possibly also surface roughness and any other inhomogeneities sample may have. Here you can see the overview of all parameters we can get out of ellipsometry. Film thickness in case of thin films due to the light interference, complex refractive index as a function of wavelengths or photon energy. We can get surface roughness, interfacial mixing, uniformity. We can do the scan of the thickness over the sample surface, obtain also optical properties mapping, anisotropy, composition, crystallinity. We can do also graded films. That means we have a refractive index depth profile. So refractive index is changing within the film. We can do also effective medium approximation films. These are films made of mixture of different compositions. And we can do also electronic transition analysis. In our institute, we are using Woolam RC2 ellipsometer. It works from 210 till 1690 nanometers, so we cover the ranges from near infrared to visible down to near ultraviolet spectra. It has wide incident angles from 45 to 90, so we can do also transmission measurements. The measurements are performed very quickly. The wall spectra is measured in less than 1 second. The spot size can be reduced down to 120 micrometers if necessary. And this ellipsometer is also equipped with automatic stages, like heating stages for thermo-optical investigations. We can do also rotating azimuthal measurements and do complete Mueller matrix element measurements, which are important for anisotropic samples. Here below, you can see precision and accuracy of this method. Data accuracy for psi and delta is very high, and thickness precision can be achieved down to 0.01 angstrom, and optical constant precision can be achieved down to 4th decimal number. Now let's proceed to see some examples how ellipsometry is providing information, characterization of yttrium hydroxides in films fabricated by A-beam evaporation. Here you can see the raw data achieved by ellipsometer. This is psi and delta as a function of photon energy for samples made at different conditions. So we have metallic yttrium, we have yttrium hydroxide, and also yttrium oxide. What is interesting here is that already from the raw data we can tell a lot about the material we have measured. For example, this red curve over here is a classical characteristic psi and delta spectra for materials which have metallic characteristics. This is due to the fact that we have no interference peaks. There are no maximus and minimus in psi and delta spectra. Psi values are relatively low, and delta is between 50 and 150 degrees. Then the green curve is typical for materials which are isolating. The same we can say also for the blue curves. These are isolating materials. They might be dielectric or semiconducting. That what should I have to note that ellipsometry for sure cannot say if we measure oxyhydride or oxide, but definitely we can distinguish if it is dielectric or semiconducting. For structural informations, we should add additional experimental methods like, for example, X-ray diffraction. From this raw data, we can also have already information about film thickness. For example, for the oxyhydride film, which has only one minima and one maxima, we can say that it is approximately 300 nanometers thin. In case of oxide, this blue curve, we have 2 times more peaks, so it's approximately 2 times thicker than oxyhydrides, 600 nanometers. For metal, we can't say any thickness because it doesn't provide any interference due to high absorption. Moreover, we can also have an information about optical bandgap. For example, for oxyhydride, we see that approximately from 3 electron volts, we don't have any more oscillations of psi and delta. That means that this material optical bandgap is approximately 3 electron volts. The oxide provides maximus and minimus even in the deeper ultraviolet. That means that bandgap is approximately 6 or even more electron volts. By applying a model, we can extract a complex refractive index of all these materials. The red curves are presenting refractive index and extinction coefficient for the metallic yttrium. Then these green curves are characteristic curves for yttrium hydroxide, and the blue curve is N and K values for yttrium oxide. This helps us to identify the A-beam evaporation conditions required to produce metallic oxide or yttrium oxide thin films. At some evaporation conditions, films with very complex optical gradients can be obtained. These are highly inhomogeneous films. As you can see here on the left graph, we have a film which can be divided practically in 3 layers, even if it is a single layer film. The sputtering conditions were such to produce yttrium hydroxide near the substrate. Then it became similar to yttrium hydroxide and yttrium mixture. And on the top we have yttrium hydroxide mixture with yttrium oxide. So it's a pretty complicated structure. We applied an effective medium approximation model to adjust the refractive index and extinction values, allowing us to describe the film's complex optical gradients, in the sense that, of course, film cannot have a free yttrium inside, but optical properties of yttrium are sufficient to make effective medium approximation of this complex structure containing varying amount of oxygen and yttrium. On the right, on this graph over here, you can see the first evidence of gradient behavior emerging under UV irradiation. You can see that the red curves are for the yttrium hydroxide which is not illuminated with UV light. The blue curves are presenting irradiated yttrium hydroxide, and we can see that refractive index is decreasing and extinction coefficient is increasing under UV irradiation. This analysis helps us determine the optimal A-beam evaporation conditions needed to produce uniform yttrium hydroxides in films without such complex gradients, which are reducing film photochromic quality. Here in this slide you can see the optical gradient revealed by ellipsometry aligns well with the XPS data, which shows an increase in yttrium and corresponding decrease in oxygen concentration towards the center of the film. Now I will show you some examples on yttrium hydroxide films fabricated by pulsed DC magnetron sputtering. By varying the sputtering pressure, we can tune the film's phase. So at low pressures, we can obtain films which are metallic, which appear dark due to low transmission. These are films with transmission almost zero over here in this graph. And at the higher pressures, we can obtain films which are transparent with properties similar to isolating materials. So over here, all these curves are presenting materials with a low extinction coefficient. The graph on the right shows the time constant data indicating a clear phase transition between 1 Pascal and 1.5 Pascal, marking the switch from metallic to semiconductor dielectric films. These plots show how the refractive index and extinction coefficient vary with sputtering pressure. At low pressures, we observe optical signatures of metallic yttrium. These refractive index curves and extinction coefficient curves are typical for metallic materials due to the fact that we have an extremely high extinction coefficient in the infrared range. And as the pressure increases, the film transition through semiconducting behavior and eventually becoming also dielectric can be observed. And it can be seen here in these typical refractive index and extinction coefficient curves, typical for semiconducting or isolating materials. So this illustrates how sputtering pressure directly influences the material's optical and electronic properties. Here you can see how refractive index and extinction coefficient and optical bandgap vary with sputtering pressure. At around 1 Pascal, we have a clear peak of refractive index and extinction coefficient over here. It is especially evident near the film surface, indicating a transition in the film optical nature. We have also observed this peak near the film substrate. That indicates that film has a slight optical gradient, and at low pressures even extremely large optical gradients. In the plot on the right, we can see band gap increase sharply with the pressure, corresponding to the shift from metallic to semiconducting and eventually to isolating behavior as more oxygen is incorporated into the yttrium hydrogen matrix. Here you can see results related to optical gradient, which I was just mentioning in the slide before. Here we reveal how optical depth profile evolves with the sputtering pressure. As the pressure increases, the refractive index gradient becomes less pronounced. So here you see we have a lower pressure, the gradient is very sharp, and as the pressure is increasing, we have a much more homogeneous thin films. The XPS depth profile at lower pressures like 0.95 Pascal in this graph over here, or 1.1 Pascal, shows that confirms the results of ellipsometry, showing strong compositional variations through the film thickness. At higher pressure, such as 2.65 Pascal, the gradient appears to be more related with the porosity. So films starting the growth, have some porosity, which is disappearing with increase of the film thickness. So this is not anymore related with the changes in composition. Now let's see some examples of yttrium hydroxide mapping during UV radiation. These are spatial maps showing psi and delta at selected photon energies. So we have here the psi as at 4, 3, 2, and 1 electron volt. The same for delta, measured at 1 per 1 centimeter large area of the sample before irradiation. And then we were repeating these measurements during irradiation. These are results for after 480 minutes of irradiation. And we can see these circular forms appearing in psi and delta spectra over the mapping of the sample. These significant changes in psi and delta clearly indicates strong local variations in the optical constants of refractive index and extinction coefficient by the UV light. Now when sample reaches the transparent state, we can see that still it is presenting the circular shapes which correspond to the area where sample was illuminated with UV light. Even if it is transparent, it still has some structural changes. Something has happened with this sample, so we need to understand what was really happening, why it was not coming back to its initial state before UV light irradiation. By applying models, we obtain these results. These maps show two key effects induced by UV radiation. Each surface map, which you see here, are different time points during exposure. On the left, we see how the light is introducing changes in the film thickness. We see a small thickness reduction under UV light, which is attributed to the lattice contraction. On the right, these are clear. There is a clear increase in the interface layer between substrate and the film. And this interface layer is characterized with a lot of effective medium approximation volume of air. So practically this film is slowly destacking from the substrate. And when it is reaching the transparent state, this separation still remains there. And due to this fact, we see these circular areas in psi and delta scan over the sample, showing that, yes, our sample didn't reach its initial conditions. This slide shows the spatial variation of refractive index and extinction coefficient at 2 electron volts during UV radiation. Each surface represented at different time slices are showing the different exposure moments. Also here, similar to the slide before. As irradiation progresses, we see a clear increase in refractive index and clear increase in extinction coefficient and corresponding reduction in the refractive index, indicating evolving optical absorption and structural changes. These changes are likely related to the migration of hydrogen and oxygen anions and the formation of vacancies under UV light. That provides electron structure modifications. Vacancies introduce middle gap or shift of the Fermi level, and these states increase free carrier absorption, contributing to higher extinction coefficient and reduces refractive index due to lower dielectric screening. So now we are at the conclusion. In this presentation you have seen that spectroscopic ellipsometry has proven to be a powerful, non-destructive tool for characterizing yttrium hydroxides in films. Unlike SEM or XPS, which often require sample preparation, vacuum conditions, or even material removal and destruction, ellipsometry provides real-time, contactless insight into optical constants and thickness of the film, depth gradient and interface changes, photo-induced effects under UV light, stability and reversibility of optical switching. Through spatial and in situ measurements, ellipsometry reveals subtle film inhomogeneities, composition gradients and phase transitions, helping to optimize sputtering conditions and identify the best parameters for high-quality functional yttrium hydroxide films. In summary, ellipsometry bridges the gap between fundamental understanding of the film and practical film engineering efficiently, precisely, without damaging the material. I want to acknowledge the funding sources supporting the research presented here. We had contributions from European and national funding bodies across 3 major initiatives: Smart Windows for Zero Energy Buildings, SWEP project, GAMART 2 project, and national project about thin films of rare earth oxyhydrides for photochromic applications. Thank you very much.